Hello, everyone. Thank you for coming, attending the session. Today we have Dr. Dino Chen from Hong Kong. He's an associate director at WSP, and he'll be talking about OpenSEES for fun. And he even wrote like a textbook for OpenSEES in Mandarin or Cantonese. Sorry, I don't know which one, but one of those languages. So thank you for accepting to present, Dr. Chen, and we are looking forward to your presentation. Thank you.
Thank you. Thank you for introducing me. And now I start, or still wait for a few minutes?
No, go for it. It's up. Yeah, you can start now.
Okay. So I will start the presentation, but just a few slides of the PowerPoint. Actually, we will have some review of the program I wrote before. Most of them is based on OpenSEES. Use OpenSEES as the calculation core, and there's a lot of function we can use. For example, the nonlinear analysis, and most of likely is a linear analysis. Because I'm a structural engineer, so I use OpenSEES as the tool for the analysis and calculation. But in the design process, sometimes for the teaching, because I'm also a teacher in the Hong Kong University, so maybe I will use OpenSEES as the teaching tool for introduce some theory to the student. And this is my introduction of me. My name is Dino Chen. I'm from Hong Kong. I'm also a structural engineer, and most likely I'm doing the high-rise building, and especially seismic analysis of the high-rise building. And in the last year, in the 2014, I wrote two textbooks for the OpenSEES in Chinese. And there's a tutorial of OpenSEES and introduce the student how to use OpenSEES for the nonlinear analysis and the dynamic analysis. And this is the version 2. In the 2014, I have an original version of this textbook. And this is my website. You can browse my website on the dinochen.com. But most likely it's in Chinese, so maybe use Google Translate. Yes, this is the two of the textbook, and now I think it's quite popular in China. There is the first OpenSEES textbook, the book to introduce OpenSEES, how to use OpenSEES. In this book, I make a small program called ETO. It means Etabs to OpenSEES, and to help the student to very easy to build the OpenSEES model based on the graphic input. Actually, it's based on Etabs graphic input and transfer the model to OpenSEES. And this is the ETO program, Etabs to OpenSEES program. And later I will give you some small introduction of this program. It's quite user-friendly for the small scale building. And I can do quite a lot. For example, the solid element and some like a bridge for the civil structure student. They want to build some large scale of the bridge model in OpenSEES. And for the bridge, I also introduced, I make some very fun program like OpenSEES bridge game. You can build a bridge on the grid. It also like some popular game in iOS system, iPhone or iPad. It's very useful for because most of the engineer cannot know the final element well, or even they don't have so many time to build the final element program, but they can use OpenSEES as the calculation core. Then they just need to build the graphic input or some script to build the model. Use the OpenSEES as a core. They can build a lot of other function like this one. I will build a bridge game. This is for the student for fun. They can use this to build a bridge model very fast, and then they can join some bridge competition, like a bridge design competition. Use the paper to make like a member. Use the paper graph. And also, I make this game is because we want to know how to do the Topo Optimization. So this game is like we call it a block structure game. Is like we use the pixel to form the structure and to tell the student how to make the structure optimized. Use the like a hand make or Topo Optimization. Use the brush. It's like a brush drawing game. It's quite fun. I will show this game later. And based on this theory, I make another game also based on OpenSEES core to try to make this topo optimization program. But this is also manual topo program. It's not the automatic, but it's quite useful to introduce the student how to the theory of the topo optimization. For example, this is the one adding point load at the top, and the base 2 point is the fixed support, and this is the traditional optimization in 2D topo optimization. And this program is based on the block structure program. Also, all the calculation is based on OpenSEES. No need to comply in C++ of the OpenSEES. We just use the original OpenSEES script to form this program. It's quite useful for you to do some fast study in structure. For example, I use this to optimize the out trigger in the high-rise building to gain the largest step list based on the limit material. So this is several program is also built in based on OpenSEES. And this is quite interesting. We use this. We use OpenSEES as the calculation code to make the program called graphic static analysis. It's another optimization for the truss structure. All this member is the 2D truss, and we use the OpenSEES as a calculation code to calculate each XO load of the member. And then we, based on the XO load and the graphic data, we transfer this truss graphic to be the static graphic status graphic. And then we use this one to make the optimization for the truss. And then it's very, I think the theory you can find the paper is written, I think it's Baker in SOM, the large consultant company in high-rise building. They have a quite certain paper to describe this theory. I think it's, but in the market, there's no commercial software to do this job. So I developed this tool to do the graphic static analysis based on OpenSEES. But because it's very easy based on the 2D truss system, so I rewrite the program without OpenSEES already. So you can see this version is without OpenSEES, but actually the previous version is based on OpenSEES. So it's quite fun to doing such a job based on OpenSEES. So I will close this PowerPoint to show you the program I write and introduce some detailed theory behind the program. Okay, and for example, I show you the bridge game. Example, the ETO I will introduce later. This is the bridge game. You can see that. Oh, it's quite small. Yeah, and in the graphic, you cannot see the OpenSEES, the windows of the OpenSEES, but actually when you build the bridge based on the graphic, and then the program will auto-gen the OpenSEES. So we draw some truss here. Okay, and then we press analysis, and then after press analysis, the program will run in OpenSEES. You can see that this is the TCL file of the program gen and press analysis. You can see that it's like a game. It's a bridge game based on OpenSEES. And the theory is when we press the design and press the analysis, the program will generate this TICO file. The model will generate the 2D node coordinate. The fixed point, I think is this 4 red point is the fixed point. And then auto generate this information of the member, like use the elastic beam column element. And then we apply the loading. Actually, the trick one is on the loading assignment. For example, for this car, go from the left to the right, and the loading is actually apply the point load at the very from the left. Sorry. Yeah, from the left here. We apply the point load at the left point is 14, and then we apply the uplift load in the adjunct point or adjunct node, and then we apply the loading. Each time we just shift the loading from the left to the right and iterate from the left to the right, and then this is the loading pattern for apply for the bridge analysis. After you apply this several case of the loading, each time step we understand, and then we collect the deformation of the data. You can see this one. This is the information of the result. You can see the record file is here. We just collect the deformation to all the range of the nodes, the deformation of the 2D, so 1, 2, 3, DOF. So the final result we display on the program and show this animation. So the theory is quite easy. It just runs like, for example, this is 20 nodes. So it just run 20 linear analysis, and to capture all the deformation of each time step and display on the 2D canvas of the program, and then make this game. So it's quite fun to make this one. It's quite easy to introduce how to use OpenSEES as a calculation core to make the like a 2D analysis program, also including the static analysis program of all kinds. And this is the bridge game. So, and how about the block game? The block game is quite very easy to use. I show this one. But this is quite large program for the OpenSEES, because for this program we use the shell element for each pixel of this canvas. For example, I set several level for games. For example, this is the cantilever. For the blue one is reference the fixed joint of the member, and this one's a loading. So this 6 element is applying the vertical loading as a point load to form this structure. So at the very beginning, I draw the very simple cantilever by drop the mouse to draw this cantilever. It's quite easy. So, and then I press analysis. You can see that the program will generate a lot of node calculation information. Close this one. I show you another program based on, let's see, this. Yeah, based on this one. Yeah, this one will show you the process. Will not delete the joint. Okay, I draw this cantilever and then I run the analysis. You can see the OpenSEES run. Yeah, this is the formation of this structure. And we can see that this is the result. We generate a lot of node deformation, and this is the script auto-gen by the program. You can see that most of them is the node location. And then we have it's quite a lot of node information because it depends on the grid. For each member, you can see that it's a pixel in the graphic, but actually it's the full node shell element here. So, and then we have the fixed joint is the blue one, and any joint in this canvas we don't use. We also assign the fixed joint for easy to program. And you can see that some part is define the pin joint is the element we use. And then you can see that we use all these elements, use shell MIT C4. And then we record all the deformation of the nodes. And then we apply the loading is the red point, and then run the linear analysis. And this is it's quite long script, but it's very easy to understand this part, the analysis theory. So how to build this model is just use the brush. It's quite fun here. You can teach students how to use your brush to optimize the structure. I show you a much more complicated structure. For example, I clean all this one. Erase, you can use eraser to erase the member. Okay, for example, level 3, this one, we can draw the truss structure like this. This is the structure, but the loading, I think, is horizontal. No, the vertical. Let's run the analysis. You can see this is the vertical point of compress this point, and the structure deformations like this. So we not satisfied of this deformation, so we maybe add two truss like this. Just for example, it's not optimized. Then you can see the score is calculate how many pixels you use for this structure. Now is the score is 1754. I think it's not okay also, so maybe we say draw more structure member like this. This is the process how to use the brush structure. We can also understand as the handmade optimization. Use menu, and this is a block structure game. And based on this theory, I transferred the program to be the Topo and Topo theory optimized program like this. And this is the model. It's much more larger than that one, but it's the same theory. We just run, for example, 0.01. This is the reject ratio for the member. This is the red point is the horizontal load ending point, and base this 2 point is the fixed point of the structure. So at the very beginning is like a shear wall. It's the 2D plate structure. And then we apply 1 point load and to review the lower stress area. After we press re-stress, we can read that this is the high stress zone, so we cannot reduce for this 3 point. But in the middle, we can reduce because it's a low stress point. And then we just double click the testing. It will reduce the shell element. You can see that this is the lump sum of the shell element. And then we can increase the reject ratio. And then we'll do it again and again. I can show you the final result of the Topo analysis. And this is the story script for document for this program. But unfortunately, it's in Chinese. I have no time to translate, so I just open this PDF. You can download from my website. It's quite detailed to describe the theory, also the script. And at the very beginning, we just build like a shear wall structure, a lot of element. The element should be very small because we need to use the average stress to represent each element. So for this program, I used the Shell MIT C4 also. And then we just, this is a regular script for the linear analysis. And we just need to know the topo procedure of the analysis. We generate the OpenSEES model, we run the OpenSEES model and make the TICO file. And then we read all the element out. This element out means the stress of the element. We combine the stress to be a meso stress, and we calculate the stress of the maximum stress, mean the meso stress of the element. We check the element, the stress limit of the element. We calculate the rejection ratio of the max stress. For example, at the very beginning, you can see that the ratio is 0.02. It means we calculate all the member to gain the maximum stress, for example, like the 10 MPa. And then we calculate the rejection ratio of the maximum stress rate stress. And then we check the stress limit is like 0.1 MPa. So for each element, the stress is lower than the 0.1 MPa. The element think that this element can be reduced, and the other part of the element can be remain. So we can see that we just reduce the element. And after several steps, we can gain the Topo optimization shape. This is the whole process of this. We apply the point load at the top and the middle point, and the base is fixed support. And then we run several steps. We gain this. Finally, we gain the Topo shape like this. Yeah, and those procedure is based on OpenSEES script, not on need to compile the C++ program. So it's quite useful. I also use this one to do the trigger optimization also. And you can try this program and apply different point location and change the aspect ratio of this 2D wall. So you can testing. For example, I increase the testing ratio. You can see the result. Yeah, this is the, but it's also manual because I think the next step version I will try to make it iterate by itself. Okay, and the other part of the fun program I introduced is the static graphic. I think it's here. This is quite useful for the high-rise building or the long-span structure analysis. Let's see. Yep. At the very beginning, we also to use OpenSEES, so we keep the code file here. But it's quite easy because it's 2D truss analysis. So at the very beginning, we also use Etabs to be a graph input. For example, like this truss, but this is not regular truss. Yeah, this is a regular truss. I think you can use YouTube to find the graphic static theory. It means use the graphic to calculate all the internal force of the member. But actually, at the very beginning, it's a very easy method to calculate the actual force for the member. But nowadays, because we have a finite element method, so the truss internal force were very easy to get by the program. But this method still useful is for the structure optimization. So for example, for this normal truss, we can run the graph analysis and to gain the graphic static figure. And how to use this one, the optimization, I can show you how to use this one. For example, for this truss, you can see that we make sure all this line reference the axial force value. The direction is the vector, but the value is the length of this one. And because you can see that this is the most optimization of the trust. For example, if I use this one, set this point, yeah, the normal trust is like this. Sorry. Yeah, this is the normal trust. When you run the graph analysis, you can find that the total length of this axial line is a certain value. For example, you can call it the energy factor is 1.229 here. So this is not the optimized shape. So we we try to move the node of the member, for example, to reduce this one, and to make this middle one is higher. Change the shape like this, we can gain another graphic. So you can see that the graphic is squished already. The graphic static figure is squished already, and the lump sum energy is reduced. So it means this structure is much more efficient than that one before. So we use this one to try to use this one to make the trust optimization tool. Actually, at the very beginning, it's based on OpenSEES to try to make the like a demo or the beta version. After we firm the theory is okay, it's easy to use by the engineer, and then we transfer to be the program itself. We rewrite the analysis code. We don't relate to OpenSEES now. So this is the application of the OpenSEES. Use the OpenSEES script. So, and the other part of the introduction, I think, is the most important is the introduce you to know the program called ETO. Actually, for the most project, if even in China, Hong Kong, I think maybe in Europe or the USA, the program called Etabs is quite popular. I think it's worldwide popular, this program. And then we try to use all Etabs as the operation system for the OpenSEES, because you can see that OpenSEES program is most likely is the script writing program for the student to run the specimen or run the text, like a seismic test or the loading test for the specimen. I think it's quite easy to build a model because the model itself is simple. But for the structural engineer, we need to build a very complicated model, at least several story building. It's very difficult to build in the script. So at the very beginning, we try to use SAP 2000 to become the transfer the SAP 2000 from the model. But at the last, we transfer to Etabs because Etabs is much more popular and most of the engineers know how to use. So I use Etabs as the program. So I show you how to run the ETO program based on Etabs from the Etabs at the very beginning. So if you want to use the version of the ETO, you can download from my website. I can show you the download address is press OpenSEES at the very beginning. The top post I think is that can be downloaded. Here is the OpenSEES information, and this is the ETO program. Don't worry, the program is in English, but this page is in Chinese. And quite direct use for the program. You just need to build the Etabs model in Etabs 9.6, I think. So I build a very simple frame structure here. Okay, like I use the default setting, several grid. So I build because the total graphic input for the Etabs. Okay, concrete section. Okay, sorry. So I assign the section to be the concrete section. Actually, we need to use elastic member, so we maybe call the E at the header of the section. Use E to automate to change the elastic section. Okay, assign the column and the beam, and then replicate to the other floor. Replicate to the other floor. So the building is built already, and then maybe we assign several point load to as a push load. So I create a load pattern called push. Then we apply the point load as a push load at the top. For example, is a push like 100 kN. Okay, and the model is built already in the graph input. It's quite easy. And then we export to, we save the model first. Say like here. No. Oh, for example, like here. Okay. Okay, save the model, and then be careful. We need to export, not E2K file, export sub 2000 S2K file. And then we save here S2K, and this is the very important file because we import is use the S2K file, and then we import this S2K file. Yeah, this import from the Etabs model, and then you can rotate the wheel. You show the 3D shape of the building. And also you can show the node number. It's quite important because we need to know the node number. We need to know the frame number. Yeah. And this, we know that for the OpenSEES, the local access is quite complicated. We use the vector. So we also need to know the vector of the member. Sorry. And this is the vector. We describe the section rotation, section angle for the member in OpenSEES. But don't worry, we will try. We use ETO. We will transfer this local access automatically, and we try to use fiber element to here, define the fiber element here. But at the very beginning, we did this tutorial. We use the elastic model, so we can select the elastic beam to describe this element. So you can see the element label. This is the element. And then we set the analysis case, but actually for me to use the ETO, I will use the test file to modify this part, but for the beginner user, you can use this one to auto-gen the analysis test script. For example, for this one, like push load 100 steps, this is the load factor for each step, like a 0.01. And then press OK, and then you can press this text file and can auto press the generate. You can see this program will gathering the information from Etabs to gen the information to OpenSEES. And this is the model basic and the node information and the mass information. This is auto calculated by the Etabs. If you need to run the dynamic analysis. And the fixed pin connection of the support point is also transferred from the Etabs, so you can define the fixed or pin support as you want in Etabs. And this is the elastic member description, the material, and the shell element and the with shell element for the wall and slab, we transfer to the ND material automatically. But in this example, you don't need to use. And this part is much more complicated for the beginner. Is the describe the section rotation or section angle for the 3D section. We transfer to the geo transfer linear for each member. So if in this model there are 1,000 members, there are 1,000 like this one description, but for the computer it's quite fast to input. And this one is the member description. We can transfer this one to be a nonlinear member. For example, I try to use this one to be a displacement beam column, for example, nonlinear beam column, and define the rebar location and press OK. And then we can generate again. You can see that we add the fiber section here, and for the member, it transferred to be the nonlinear beam column here. And this is automatic to generate. So for the student, for the beginner, it's quite easy to build a model and make them understand how to build a model in this script. And then after that, we could record the file. And this one, because for the out, we can see that we just click the deformation for the all nodes. We also can generate the element force for the frame, and the other part you can handwrite for the other recorder you want. And the push load is transfer from the Etabs. You can see that is the X direction apply 100 kN for the top 4 point. And then the other part is the analysis script usually you use. And this part you can modify by manual, by editing the text. So you can generate this. After generate this one, we can save, select all to save the test file. For example, you can also press the save file to the script. For example, this one. Yeah. And I show you how to run this script. The thing is, OpenSEES program example. Yeah, you see that this script is generated from that one. Yeah, I just keep 100 time steps for this analysis. For example, run this one. Source auto and finish. And after finish, we can generate all the node deformation in the single one file called node0.out. And we can use the program ETO to plot the deformation also. We can import the model we import here. And then we run. Yeah, maybe this is not the same model again. Run again. Maybe need to generate and not the deadload and set. Here is push 0.01. Okay, and generate the new text file. Save. CO. Okay. It's here. Okay, run the file again. Oh, I need to remove the ND material because we don't have any shell here. So, okay, and then we read the deformation. For example, we read the deformation is based on the not out. Time step is 100 maybe, and step is like a scale is 100. Just for example, yeah. So it's not big enough. Yeah. This you can see the deformation. The scale is 50,000. Okay. Also, you can show the animation. This is a new function I added recently, and time step. Yeah, it's okay. And then not here. It's quite. You can see the animation. For the presentation in like a paper or the PowerPoint to describe the information in the research, I think this is a useful tool for them to do the post for the OpenSEES. Also in this program, also can do the show you the ETO another function to. I think it's most likely the geotech student to. I mean the do the research of the geotechnical analysis. They want mainly use the solid element for the OpenSEES, not the frame element we use for the structural analysis. This one it also can do, but unfortunately, Etabs cannot model the solid element, so we need to use step 2000. You can find the example here on the website. Not this one, sorry. I think it's 30. Oh, I'll show you the website. Solid element, I think the sample is here. But this one is like an abacus or ANSYS. They're typical solid element model. It's a hinge model. You use a solid element, and then it's 24. I see. Okay. Yes, 24. I can show you the PDF. So 24. Oh, I see the scroll bars here. There's quite a lot of different type of analysis in the textbook. So I'll show you some classical, like 24, 40. What's this sample? Shear wall structure. So the '18. '21. Yeah, 24. Okay, in SEP 2000, yeah, this is the problem description, and we need to run this solid element analysis, apply the 300 kN on this point. This is the solid element. We use SEP 2000 to build this model, and then we transfer to ETO like this, and then we also generate the model by ETO. In this model, we use the STD brick element, which I think it's 8-node element, and then run the linear analysis to try to make the OpenSEES to be like an abacus or ANSYS program to run the solid element. But also this one can be used in the geotech research, because geotech also want to build quite a lot of solid element, and show you how to use this case. I think here. yeah, at the very beginning we use SEP 2000, and then we have the, sorry, here, solid element. So you can see SEP 2000 is the, I can show you SEP 2000. Yes, like this. It's a solid element in SEP 2000, and then we export the file to be STK file. Select Alt, okay, generate the model 1 S2K. But in ETO, they need to transfer the SEP 2000 file to be another type of SEP 2000 file. So we open the SEP VS14 to 6 VSEP, this one. We open the solid element SEP 2000. Yes, okay, yeah. Then we set another version, SEP 12, for example, and then we import from the model. Yeah. Oof. I think it's something wrong here. I think the unit problem. And then we just describe this example. Okay, and I think the presentation is most like this. Can show you some picture of the, because this textbook is in Chinese, but can show you the picture of the tutorial of this book, my textbook. And for the very beginning is some basic theory of the OpenSEES, especially the nonlinear element. It's like a normal textbook, but after this part, the chapter 3, we introduced the ETO program to introduce how to build the model in ETO. And this is the introduction. And the very beginning, we have the tutorial from 1 to 20. I think now the textbook 2 is 35. So the textbook, in the textbook, the tutorial 1 is the truss structure, like a bridge truss. And the tutorial 2 is the frame structure for the elastic analysis. And also to teach how to use rigid floor diagram in OpenSEES. And then we have the teach how to calculate the local axis for the, or also called the local vector for the section rotation. And then we have the plastic hinge model for the simple beams, simple support beam, but it's nonlinear. We show how to show the plastic hinge. And for the example 4 to 6, I think it's the frame structure, including the pushover analysis, the frame structure, and the nonlinear analysis for pushover to generate the pushover curve. For the example 5 is the model analysis to find the natural frequency and the mode shape for the building. Also use the ETO. And the 6th tutorial is use the time history analysis, but it's an elastic model. To run the time history analysis to teach students how to import the time history ground motion data to the OpenSEES and define the damping ratio for the building. In here is the relay damping theory. And for the example 7 is the critical one, is the nonlinear time history analysis example, also based on the ETO. And then for the 8 is the pure steel structure, like a structure brace. For the brace, we consider the geometric nonlinear. So you can see that we divide the member in pieces. And then we try to introduce the cycle loading, push and pull. And to run the model is consider the geometric nonlinear and the non-geometric nonlinear. And also we try to introduce to use OpenSEES as the geononlinear analysis tool to run the large deformation analysis for the like a shell member, shell truss. This is the shell truss. We can find the jumping buckling. We also introduce some very simple nonlinear member like only compression or only tension link or truss. This is for foundation, only compression link. And for the gap, we also introduce how to use gap here. And to introduce how to use the hinge in OpenSEES is quite different between OpenSEES and Etabs and SEP 2000 for the hinge and how to treat the hinge situation. But we can use ETO to very easy to model the hinge, the pin. And also we also teach students how to use shell element. This is the elastic shell, as I think it's MIT C4, and build a very complicated truss model. Use the 3D truss, like we call this as the web truss in China. It's quite common. And also in this model, we introduced the 3D three direction earthquake mode, earthquake loading, like a USUI and UC, to run the linear analysis, nonlinear analysis for the space structure. And also the P-stress beam using OpenSEES P-stress beam and the bridge. And from this one is the civil structure like a bridge. This is the long span bridge. We consider the two joint support to have a different excavation. So we modify the earthquake transfer from one point to another point, have a different start time. And then we have this complicated model also built in SEP 2000 and transferred to the ETO. So even this model can be run in the ETO to transfer the script from ETO to OpenSEES. And this is the two deformation of the two supports to model the base shear is start from the different point. It's quite complicated for this example thing. And we use shell element to, and this one is the displacement nonlinear beam column element to model the shear wall. It's not the, sorry. Okay, and the shear wall. Yeah, and this is the large scale model is to build the frame shear wall structure. For the example, you use the ETO to build this several story building and to run the pushover curve. We compare to perform 3D to make sure the calculation is correct. And this example is for the building use a viscous damper. And the other part is compare with the Etabs, use viscous damper. And the 20 example is use the isolator in OpenSEES. And the other part is how to make the OpenSEES second development as the calculation core, for example, like to generate the spectrum from the ground motion data. And the other one is transfer the OpenSEES to be a PM curve analysis tool. The PM curve tool. This is the old version of the PM curve generated from OpenSEES. And solid element we already introduced to you to use SEP 2000 as the peer model tool. This is the, and also we use the SEP2000 as the 3D steel joint. This is very common use in structural analysis. We need to build a steel connection to verify the stress limit for the steel joint. We also use OpenSEES as a tool to analyze this one. And also we use UTO to build this complicated shell element and run the nonlinear analysis to justify the fixed connection of this joint. And the large-scale bridge model, this is the bridge model to consider how to calculate the influence line for the bridge. And I think it's quite large model in my textbook. And this is the version 1 textbook, the content of the version 1 textbook. I think it's quite a lot of content. If you have interesting, I can browse my website. There's quite a lot of TICO file in the website and the model description in the website. So I think, Pavan, hand over to you. The presentation is over. I would like to hear the comment and the question from you guys.
Thank you for the presentation. It was good. Okay. Yeah. Presentation. It was good. And any questions from anyone? Does anyone have any questions? Feel free to ask. So, I mean, you have a question? Go for it.
Yeah. Hello, Professor Dino Chen.
Yeah.
I have a question after I hear your presentation. For your second tool, those brush tool, and I wonder what material. No, not this. The second one, brush.
The shell one.
The shell one, yeah. I wonder what's the material you used for this game?
I think you use double check. And main thing is steel element, elastic steel. Yeah.
Okay. Cool. Thank you.
You have any other questions?
No.
Any questions? So, I mean, I'll ask you a question. I was curious, like when you use the Etabs to OpenSEES thing, you made your model in Etabs, and how did you convert like that into the OpenSEES code from the Etabs, that S2K file or whatever you used? Can you explain that one, please?
Okay, and in it, after we build the Etabs model, the Etabs will generate the model 1 S2K file. I can open this file.
You wrote the code for that, or the Etabs does it?
Yeah, this is from Etabs.
Oh,
it's
okay.
Quite old version SEP2000 format, but it's quite simple. It's quite similar to the OpenSEES. You can see that this is the joint. We can transfer all the joint information to be the node information to OpenSEES. It's quite the same. And the fixed support, you can read the restraint is quite similar. And the mask, also the mask is quite similar compared to OpenSEES and the S2A file. But this S2K file is from Etabs, not from SEP2000.
Okay.
And you can see the frame file is quite exactly the same as the OpenSEES. So we find quite a lot of different models. Find that the S2K file is much close to the TICO file in OpenSEES. So we transfer to make this tool.
So how did you transfer this to the TICO file?
I used the program called at the very beginning we call the Lazarus. It's a Pascal language to read the file from from the SPA file to the tickle file. I think now you can use Python. I think it also can do this procedure. The complicated one, I think, is the generate the geotransfer data like this one.
Geometric transformation.
Yeah.
Okay.
Yeah, it's much more complicated for this part, but the other part I think is quite easy. At the very beginning, as I'm a student, at the very beginning we use the Excel file to generate this model, but the efficiency is quite low, so we transfer to be a program.
So how did you get the geometric transformation part, like the code for this one? Like how did you automate this part, like the geometric transformation part?
Oh, we just read the, for example, we just read the information to the program like object, for example, the node and the frame. And then we generate, we just rewrite the format of the output, and then it's quite simple, direct to generate this part. You can find that the each number is the same.
No,
it's just the format is different.
For the geometric transformation.
Yeah, geometric transformation I described in the textbook. I think we have.
Okay.
We used a bunch of cycle sign method to transfer. I can't quite remember.
Okay.
I can show you the text here. Yeah. Yeah, for the vector and for the Etabs, they only have one parameter called angle, degree of the angle.
Okay.
And then we need to transfer to this vector called we call the unit vector for the your transfer.
Yes.
And we just need to calculate by this side, like a cycle sign method. For example, it's 30 degree. We just calculate to be like at this part, I think it's sine 30 degree, and this is a cosine 30 degree and sine 30 degree for the column. And for the beam, we need to rotate to another axis from the joint I to the joint J to calculate the other angle. This angle is 2D angle. We call it the alpha, and the other angle is maybe beta. So it's a bunch combination from a cycle sine equation based on two angles. One is section angle, the other is the line angle, to calculate the geometry vector. I think we have a calculation equation based on the global axis is the Z value is represent the elevation height is Z coordinate, and then we have a calculation equation. I'll show you later maybe.
And the ETO itself, like once you loaded it into the ETO, your own tool, how did you make like that tool, like using C++ or Etabs?
Oh, you call this program actually.
Yeah, the ETO thing.
I use Lazarus.
Okay, Lazarus.
Yeah, it's an open source program.
Okay.
Yeah, it's quite nice to build a graphic program.
Ah.
But it's based on the very old language called Pascal.
Okay. So using Pascal, like this one, you created that interface where you can do the deformed shapes and everything, right?
Yeah.
Okay.
Yes.
And it will run, like once you run it, and in the background it will run in OpenSEES.
No. I just transferred to be a text file. No, sometimes we run OpenSEES is in the background, but ETO no need to run the OpenSEES. ETO is just show you the.
So once you run it on ETO, in the background it doesn't run in OpenSEES.
Yeah, you can, for example, you can run show you the model. Yeah, we just generate the text file, and then we run based on this text file. Actually, we can run OpenSEES here, but we seldom use this function because
Okay.
we need to have to modify some material, some analysis code. We also need to manual to modify in the test file. So most of the function we use is just generate the test file.
And run OpenShell. Okay.
Yeah. And the other part of the program will show you like a bridge game. We just run the OpenSEES at the background. Yeah.
Okay. Oh, cool. So once you run it in background in the OpenSEES, then you'll again load the results into this and then check the results. Okay.
Yeah.
Okay.
Most likely the procedure for every program is like this.
Yeah. Oh, awesome. I mean, sounds cool. This is the first time I'm seeing this. He was telling he was using this since forever, so I didn't know that.
Yeah, because the test file in Chinese, so seldom foreigner will maybe know this one.
This is actually super friendly. That's awesome. Yeah.
Yeah.
Thank you. I mean, anyone has any other questions? So you can use any materials or any elements, any type of things for these sections, or are we limited by any amount of sections or?
Yeah, for the section, I think in the program before we have these several type for elastic nonlinear beam column and displacement beam column, beam with hinge, and the Timoshenko beam, I think, and the truss also, and these several type. And no more new, but you can use the Excel file to modify the test file to if you have some new element.
Yeah, you can directly change the text.
You can modify.
File. Okay.
Yeah.
Okay. Cool. Makes sense.
It's not total automatic. It can be automatic and some manual.
Yeah. Okay. I'm just trying to understand how it is. Cool. Sounds really cool. Any other questions from anyone? If not, then like I think. Any questions? You have any more questions? No. Okay, cool. I mean, if no one has any questions, then we will end today's session here. Thank you, Dr. Chen, for the presentation. Like, it was really helpful, and I mean, hopefully, you'll develop more tools, and we'll have one more